Very fortunate today. We have Nicole Younger Halpern, a fellow from the Joint Center for Quantum Information and Computer Science, which is joint between University of Maryland and National Institute of Standards and Technology. She's a theoretical physicist at the National Institute of Standards and Technology and an adjunct professor at the University of Maryland. She earned her bachelor's degree at Dartmouth College, where she graduated as co-valedictorian of her class. As a Perimeter Scholars International student, she completed her master's at the Perimeter Institute for Theoretical Physics. Nicole earned her PhD under John Preeskill's auspice at Caltech. Her PhD dissertation won the International Elias Pergon Prize for a thermodynamics PhD thesis. As an ITAMP postdoc fellow at Harvard, she received the International Quantum Technology Emerging Researcher Award, and she has received also the U.S. Aspire Prize for Young Scientists, the Mary Somerville Medal, the Herman Weil Prize for Understanding Physics Through Symmetries, and the Catherine B. Gebbe Young Investigators Award from Sigma Chi NIST. Additionally, Nicole has been included in the Science News 10 to Watch list of early and mid-career scientists. She is the author of the book, Quantum Steampunk, which I have here, and I recommend. Very good book. Looking forward to hearing her today on that. That book won the Prose Award for Popular Science and Mathematics. Younger Halpern also publishes a blog per month on Quantum Frontiers, the blog of Caltech's Institute for Quantum Information and Matter, for over 10 years. Been very busy. So welcome, Nicole.
Okay, you're on.
Thanks very much for having me. I mentioned I was first in this building in 2009 when I was an undergraduate, shortly after declaring my physics modified major. And I haven't been back since, so it's a delight to be here. Okay, so you might be wondering about this unusual image on the cover slide. And it's here because I think of this talk as really not my great-great-grandmother's thermodynamics. To start with, what is my great-great-grandmother's thermodynamics? This idea was captured eloquently in an article by a writer, Sam Keen. He said that when he was an undergrad and he started a thermodynamics class, it started with a quote from Einstein. Thermodynamics is the only physical theory of universal content which I am convinced will never be overthrown. When a writer, as a student, heard this, he thought, wow, this sounds really exciting. I'm looking forward to it. But even Einstein's imprimatur couldn't glamorize the grubby details of heat and work exchanges. So, at least according to this writer, although thermodynamics is arguably the most successful scientific theory in history, virtually no one cares because they're also bored by it.
So I guess that, I don't know if it was in your book or whatever, that someone said that the only two things that are certain in life was taxes and the second law of thermodynamics.
Indeed, it's an important law.
Yeah.
One of my favorites. So perhaps I will be boring you for the next 45 minutes. Well, let's take a step back and talk about what thermodynamics is. I find that a lot of physicists don't know the definition. So it's the study of energy, the forms energy can be in, the transformations amongst those forms, and temperature.
But by the way, I'm a chemist.
Okay, so you probably know better than most of the physicists do.
Probably, but that's not saying much.
That's because he's a chemist.
At least Yeah, chemists sometimes have a better record with this.
Yeah, well, it work with it more.
Yeah, exactly. So another complaint by this writer was that the name thermodynamics evokes images of Victorians in stuffy suits tinkering with steam engines. I agree about the Victorians, I agree about the steam engines, but I think probably not all of them were stuffy. But he is right that the Industrial Revolution inspired thermodynamics. Since the steam engine was powering factories and changing the face of civilization, it makes sense that people wanted to understand how efficiently these machines could work. But these practical questions led to fundamental questions like, why does time flow in only one direction? And also, maybe arguably had some influence on some of the literature of the day. So another complaint of this writer is that thermodynamics is a far cry from the enigmatic koans of quantum mechanics, which are relatively easy for a lot of people to see as inherently fascinating. The enigmatic koans of quantum mechanics over the past few decades have been codified in the field of quantum information science. And by quantum information science, I mean the study of how we can use quantum phenomena to process information in which we can't if we have just classical systems. By quantum physics, I mean a whole lot of things. So entanglement between particles, how operators can fail to commute with each other, the discreteness of spectra, how measurements disturb quantum systems, and even more phenomena. I also mean a number of things by process information. So solve computational problems, communicate information, secure information cryptographically, and store information in memories. Just as there are information processing tasks, there are thermodynamic tasks, like powering cars and charging batteries and cooling systems. So we can ask, since quantum phenomena can enhance information processing tasks, can they also enhance thermodynamic tasks? For instance, we can design quantum engines. And according to certain metrics, in certain situations, they might be able to they have been shown to outperform certain classical counterparts. Also, the laws of thermodynamics were developed by people who had in mind steam engines, large classical systems. So it's worth checking how and why they extend even to quantum systems that entangle. For instance, we can use tools from quantum information theory to prove more refined, more precise variations on the second law of thermodynamics. And finally, we can look at a system that's processing energy and ask, which of its behaviors does it exhibit only if it's not in classical? So we can use thermodynamics to understand better where the boundary is between the quantum world and the classical world. I consider these to be the guiding question of quantum thermodynamics, a field that has experienced a great deal, I wouldn't quite say a resurgence, but a great deal of energy over the past decade and a half. The influence in the community have exploded. If you're interested in some references about the field as a whole, I can point to these 3 reviews that cover textbook and reviews that cover the recent quantum information influenced version of quantum thermodynamics. And then there is this book, which I wrote for the general public, but the general public does include scientists. And I should probably spend about a minute on the steampunk here. So steampunk is a genre of literature, art, and film, and it has Victorian settings, settings from the 1800s. So the Wild Wild West, Sherlock Holmes's London, La Belle Epoque in France, but also futuristic technologies. So time machines, automata, dirigibles, submarines. It has this blend of the old and the new. And I think of quantum thermodynamics as the real world version of steampunk, because thermodynamics was developed in the 1800s, but quantum information science is cutting edge and to some extent futuristic. We still don't have large scale quantum computers. So kind of to amuse myself, I peppered this talk with steampunk art. So if steampunk isn't your favorite aesthetic, then I apologize. But it kept me entertained, so hopefully it'll at least keep people awake. Right. The majority of this talk is inspired by a basic problem in undergraduate statistical mechanics. Here, we think about a small system interacting with a big environment. The two exchange things. If they exchange just heat, the small system may thermalize to a canonical state. When I say state in this case, I mean quantum state or density operator, so a matrix expressed relative to our favorite basis, or a trace one positive semi-definite linear operator. And the trace one means if we measure the system, we'll get some outcome. Positive semi-definites, I mean, all of the eigenvalues are real and at least zero. So I'm not just referring to a wave function or a pure quantum state, I'm referring to an arbitrary quantum state, which could be pure or mixed. And if our system and environment exchange heat and particles, then the small system may thermalize to a grand canonical state. For instance, if we have a cup of tea, we put it on a table, we expect that it will exchange heat and H2O molecules with the surrounding air until the two come to be at the same temperature and chemical potential. And we can play this game with a number of different quantities that are exchanged and a number of different thermal states. These things that are exchanged are conserved globally, so I'm going to call them charges. I'll denote them by Q and index them with A. This exchange process matters because it is the process of thermalization, which is ubiquitous, happens all over the place, unless there's something special to stop it, like the input of work. And this thermalization goes hand in hand with the arrow of time. Now, these exchanged things are represented in quantum statistical mechanics with Hermitian operators, and it turns out that in some important arguments in thermodynamics, we implicitly assume that these Hermitian operators commute with each other. This assumption is implicit. For instance, it was not mentioned in my undergraduate statistical mechanics class when we derived the form of the thermal state, but it is in there. But one of the most fascinating features of quantum theory is the existence of operators that don't commute with each other. This non-commutation leads to measurement disturbance and uncertainty relations. So we're really obliged to ask, what happens to thermodynamics if thermodynamic charges don't commute with each other? This question led to a small growing subfield. And if you're interested in learning about the field as a whole, I can point to this forward-looking review. So here's where I'd like to go in the rest of the talk. First, I'll present a concrete example, so we all have a picture in our heads. Then I'll give a brief historical overview of this little subfield. I'll talk about what changes in thermodynamics when charges don't commute, and then talk about the opportunities for future work. Here's a concrete example. It was proposed in this theory paper. It was then realized experimentally in the lab of Christian Roos and Rainer Blotz. They have a trapped ion lab in Innsbruck, Austria. And then a generalization of the theory was introduced in this paper. So consider a chain of qubits or quantum two-level systems, for instance, realizable with trapped ions. We can regard a small subsystem, maybe two of the qubits, as the system of interest. The whole thing can consist of n copies of the small subsystem, so that the other copies form an effective environment. The whole thing forms a closed quantum many-body system of the sort that's been studied experimentally and theoretically a great deal over the past few years. To introduce charges, I'll introduce the notation sigma aj to denote the eighth component of the spin of qubit j. We can have charges that follow from summing the spin components across the lattice. And we need a Hamiltonian, we need dynamics that have three properties. First, the Hamiltonian should conserve all of these non-commuting quantities globally. Second, the Hamiltonian should transport the quantities in between subsystems. And third, the Hamiltonian should be non-integrable, so it should not be too constrained, or it should not constrain the state too much, so that the state of the whole system can explore the whole subspace available to it, if we want to make statements and draw conclusions about thermodynamics. So we can build such a Hamiltonian. We learned in undergraduate class the forms of the raising and lowering operators for the z components of the spin. We can put together an operator that takes one quantum of the z component from site j plus 1 and hops it onto site j and does the reverse in superposition. And we can build analogous hopping operators for the x and y type charges. When we put together the total Hamiltonian, we want to take that hopping operator, we want to sum it over the charges, we want to sum over the lattice, and introduce a hopping frequency. You might recognize this factor as the Heisenberg interaction. The Heisenberg interaction has been well known for a long time. It's, as illustrated, for instance, here, it can be simulated experimentally. Although I like the fact that even just within the past decade or two, it was found to exhibit anomalous transport. So I'm hoping it'll have more secrets for us. But if you're still bored by the Heisenberg interaction, which granted, I'd never seen written in this way before to indicate that explicitly it conserves non-commuting charges globally and transports them locally. And I can point to this theory paper down here. In that paper is a generalization of this process for constructing a Hamiltonian that conserves non-commuting charges globally and transports them locally. So this process extends to a number of other, many other sets of non-commuting charges. If we want to, I'm not sure why this isn't working anymore. I do have an extra battery, so let me try that. No, okay. Clicker just doesn't want to work anymore. All right. If we want to make this Hamiltonian non-integrable, then we can either give the lattice more than one dimension, or we can add couplings beyond nearest neighbor. So this is a concrete picture to keep in our heads. Are there any questions about it?
No, not now.
Okay.
So just one. So can these be thought of as electrons with spins? I mean, that's just what the picture sort of, and they're interacting with each other, like getting entangled, or?
So we have a bunch of qubits. These can be realized with trapped ions in the experiment here. Each qubit, each quantum 2-level system consisted of 2 Zeeman levels. And we can define a sigma x, sigma y, and sigma z associated with those. So we can think of these 2-level systems as exchanging x components of their spin and y components and z components.
Okay.
But here's a brief historical overview of this little subfield. The first work that I know of that treated anything like non-commuting charges in thermodynamics was this 1957 paper by E.T. Jaynes. In it, he codified the principle of maximum entropy for quantum systems. We use the principle of maximum entropy when we want to identify, well, sometimes when we want to identify the form of a thermal state. It's the state that has the greatest entropy of all of the states that satisfy certain constraints on the system that we know. One constraint on every state is normalization, but we might also know, say, the average energy and average particle number of a system. The von Neumann entropy quantifies our average uncertainty about an outcome of a certain measurement of the state. So we can ask, which is the state that upon satisfying these constraints achieves the greatest entropy? And the answer is the grand canonical states, which is the thermal state that's appropriate when energy and particles are conserved. James noted that the principle of maximum entropy works even if the observables we know about don't commute with each other. And that's most of what he said. He wrote only one paragraph. So when I read that paragraph, I thought, no, this is the most interesting part. Nobody in thermodynamics ever talks about what happens if these quantities in this, things like the thermal state derivation don't commute with each other. But this non-commutation is so important for quantum physics. For instance, James didn't talk about how thermalization to this state might happen, and he didn't talk about which sorts of systems could thermalize to this state. He had some acolytes who tried to complement his very information theoretic derivation with a more physical derivation, but they ran into a mathematical problem. Over the next few decades, as far as I know, nobody talked about this problem at all, although there were some developments, mathematical developments in quantum information theory that later proved useful. Then about a decade ago, at the intersection of quantum information theory and quantum thermodynamics, some of us started to notice that some arguments broke down if conserved quantities failed to commute with each other. That spurred 3 groups across the world simultaneously to try to justify writing down a thermal state in the presence of non-commuting charges, because it wasn't even clear that writing down the state would make any sense from a physical perspective. But we all agreed that it makes some sense to write down the thermal state. But we call it the non-abelian thermal states. The non-abelian is here because the conserved quantities generates a non-abelian algebra. And this state has the form you might expect of a thermal state. So it's an exponential. It has here beta, an inverse temperature. H is a Hamiltonian. The sum is over the charges. Mu A is an effective chemical potential associated with a charge QA. And Z is a partition function to normalize the state. Over the next few years, non-commuting charges started spreading across the intersection of quantum information theory and quantum thermodynamics, and more recently have started spreading out into adjacent fields in many-body physics. So what have we found out? What changes in thermodynamics when charges don't commute with each other? I'll present a small glimpse of what has been learned by the community by this point. And the main takeaway of this part of the talk is it's not clear that the small system thermalizes just as usual when charges don't commute with each other. And this claim should surprise us because, again, thermalization is ubiquitous. It usually takes something special to change thermalization or make a system resist thermalization, such as the input of work or maybe a special regime of matter. So 2 derivations of the form of the thermal state break down if charges don't commute. Also, if the charges don't commute, then the global charges don't share an eigenbasis. So they don't necessarily share an eigenspace. It's a shared eigenspace that can serve as a microcanonical subspace. And I should review what a microcanonical subspace or state is and why it matters in thermodynamics. Let's go back to the simpler problem in which a system and environment exchange just heat and particles. Suppose we want to convince ourselves that the small system is in the thermal state. Then we'll suppose that the whole system has a well-defined number of particles. So the whole system is in a total particle number eigenspace. And we'll suppose that the total energy has a pretty well-defined value. So that space is a microcanonical subspace. We ascribe to the global system a state that's a microcanonical state. So it's the projector onto that subspace, normalized by the dimensionality of the subspace. We trace out the environment to identify the reduced state of the system of interest. And that state turns out to be the grand canonical state, the appropriate thermal states when energy and particles are conserved globally, if the system and environment couple together just weakly. But suppose that our system and environment exchange more charges that commute with each other. Then the microcanonical subspace is an eigenspace shared by all of the global charges. Apart from the global Hamiltonian, the Hamiltonian is special because it generates the time evolution. But if the charges don't commute with each other, then, as we said, they don't share an eigenbasis, they don't necessarily share eigenspaces, or they probably don't share many eigenspaces at least. And so we can't rely on the microcanonical subspace. So we can't rely on one of our earliest assumptions in the argument we use to convince ourselves that the small system is in a thermal state. Right, back to our list. If the global Hamiltonian conserves non-commuting charges, then it will have degeneracies. So some of the energies will equal each other because of Schur's lemma or resultant group theory. And degeneracies tend to throw wrenches in arguments for thermalization type behaviors. Oh. Suppose that we have a metal rod with a hot end and a cold end. Heat is going to flow on average from hot to cold, and as energy leaves a subsystem or enters a subsystem, it generates entropy. This entropy goes along with thermalization. Now suppose that instead we have a subsystem with one set of effective temperatures and another subsystem with another set of effective temperatures, so that these two systems can exchange quantities that don't commute with each other. Again, whenever a quantity leaves a system or enters a system, it produces entropy. And the entropy production turns out to be decreased, even on average, by the commutator between charges. So non-commutation of charges can decrease entropy production at least or even on average, and so hinder a facet of thermalization. This result is by a colleague of mine at Duke. He was considering local operations, say two-body interactions. And also, suppose we have a whole bunch of particles, let's say n particles. We can also imagine the set of all n particle unitaries that set of particles could undergo. Suppose first that there is no limitation on which two-body interactions can happen. The two-body interactions can implement all of the n-body interactions. This is why quantum computers are called universal. But suppose that now the two-body interactions are constrained to conserve some charges. And now consider the set of n-body unitaries that conserve the same charges globally. Now,
could you say exactly what global unitaries are? Because I don't.
A unitary that acts on the set of all n particles. So when I say global in this specific context, I mean n particle.
Okay.
So I have a system of n particles, and the system of n particles can undergo a unitary operation. So I would call that unitary operation an n particle unitary, because the whole system evolves under that unitary. So suppose that the two-body interactions are constrained to conserve some charges, and consider the set of n particle unitaries that conserve the same charges globally. Now the two particle unitaries cannot implement all of the n particle unitaries. And the constraint is even more severe if those charges don't commute with each other. So the non-commutation of charges limits which n particle transformations can be undergone as a result of local two-particle, physically feasible interactions. And so the non-commutation of charges limits something like the chaos achievable by local interactions.
When you say they can't go from one to the other, does that mean that if you sit there and watch them interact with each other, there are states that they can't get to?
Yes,
Oh, that's what you're saying.
it's an equivalent statement.
But if somebody came in from outside and disturbed the system, they could go to another state that, or you're saying that there are impossible states that they can't exist.
I'm saying, suppose that we have a system of n particles, and there are rules for which interactions the particles can undergo. For instance, suppose they can undergo only 2 particle interactions.
Okay,
And suppose that those interactions are constrained to conserve certain quantities.
okay,
Then we can ask, which evolutions can the entire system undergo as a result of these 2 particle interactions?
okay. So you're saying that pathway, there's no pathway for them to get there. There's impossible situations for them to arrive at
Yes.
if you just watch them. Okay,
Yes,
all right.
exactly.
Is this then a quantum version of Fermi pasta Ulam?
I would have to review Fermi pasta Ulam. I last dealt with it a number of years ago.
Yeah, I mean, it's a thing where they thought, it was a nonlinear dynamical system, pretty classical, ran it in a computer, figuring the whole thing would become ergodic and effectively, in my mind, thermalize, but it didn't. The nonlinearities in there somehow, okay, it would do oddball things, but it didn't completely cover phase space. So this sounds to me like this is a quantum version of whatever was restricting their nonlinear model from becoming ergodic. It sounds like this is restricting, in a quantum sense, restricting the system from becoming ergodic.
The way I think of this is we know of a few mechanisms to stop a many-body system from thermalizing. One of them is FPU. One is many-body localization in the quantum realm. One is just ordinary integrability. And the community is in the process of exploring to what extent non-commuting charges form another mechanism for hindering thermalization. I'll talk about this more at the end of the talk.
Great, thank you.
Okay. The 6th point I'd like to talk about in some more detail. It is that non-commuting charges conflict with a really useful toolkit that's been introduced in quantum many-body physics. This toolkit is called the eigenstate thermalization hypothesis. First of all, it has a horrible number of syllables, so sometimes it's abbreviated as the ETH. I try not to use acronyms much in talks, but sometimes it'll be necessary because this is a huge mouthful. The eigenstate thermalization hypothesis is in a toolkit that's used in many subfields of quantum many-body physics, and it helps us understand why a closed quantum many-body system thermalizes internally when governed, in most cases, by a non-integrable Hamiltonian. Suppose that we have a quantum many-body system and we measure some typical local operator O. We can represent that operator as a matrix relative to the energy eigenbasis. That matrix has matrix elements. The eigenstate thermalization hypothesis is an ansatz for the forms of the elements of this matrix. Suppose that we have a Hamiltonian and an operator O that satisfy the ETH, and suppose that the Hamiltonian does not have degeneracies, and suppose that we prepare our quantum many-body system in a microcanonical subspace, which we talked about earlier in the talk. Then we can show that the system will thermalize internally in the following sense. Suppose that we measure this operator O at a time t, we take its expectation value, and then we average the expectation value over time. The time averaged expectation value will equal the thermal expectation value to within small corrections. Here, n denotes the size of the global system, and the corrections are like 1 over n. Also, in this talk, when I write O, I'll mean scales as. We said earlier that if the Hamiltonian conserves non-commuting charges, then the Hamiltonian will have degeneracies, and we can't rely on microcanonical subspaces. So what about the ETH itself? It turns out that non-commuting charges conflict with the eigenstate thermalization hypothesis. From now on in this part of the talk, I'll focus on conserved charges that are the components of angular momentum, as in the concrete example that we talked about a few minutes ago. We said that the ETH is an ansatz for the forms of the elements of a matrix that represents a typical operator relative to the energy eigenbasis. Problem is, the Wigner-Eckert theorem dictates the form of this matrix. The Wigner-Eckert theorem is something we learn in grad school on the way to a PhD qualifying exam. And then some people don't use it ever again afterwards, some people do. I don't have time to present the whole Wigner-Eckert theorem, but I'll present a simple example that illustrates it. Suppose we have an atom with some amount of angular momentum, and suppose that a photon kicks the atom. Then afterward, we measure how much angular momentum the atom has. What is the probability that we'll get some particular outcome? Or more precisely, what is the probability amplitude associated with getting some particular outcome? This probability amplitude is the product of two particular factors according to the Wigner-Eckert theorem. The Wigner-Eckert theorem butts heads with the ETH because this probability amplitude, as a matter of fact, is an element of a matrix that represents an operator relative to the energy eigenbasis. So both the Wigner-Eckert theorem and the ETH are trying to dictate the form of this matrix element. That's why they butt heads. Now, the Wigner-Eckert theorem is a theorem. We know it's true. In contrast, the ETH is just an H. It's just a hypothesis. And so it loses out to the Wigner-Eckert theorem. So here were our premises in our arguments for the internal thermalization of a quantum many-body system. And that was what we meant by thermalization. Non-commuting charges knock out all of the premises. So what do? Do we have to abandon the ETH entirely? It's been very useful across many-body physics for many years. I had the privilege and pleasure of working with Mark Schrednitsky's group in Santa Barbara on a non-abelian eigenstate thermalization hypothesis that we recently checked numerically together with Jae-Dong No, who is at the University of Seoul. So I'm going to present a cartoon version of the non-abelian eigenstate thermalization hypothesis, since this is a colloquium style talk. Again, suppose we have some quantum many-body system, and we've identified some local operator of interest, O. Suppose we represent the operator as a matrix relative to an energy eigenbasis. According to our hypothesis, this matrix element has this form. It's a coefficient times the sum of two terms. One term is called the diagonal term because it's non-zero only on the block diagonal of the matrix. And the other term, very creatively, is called the off-diagonal term because it can be non-zero also off the block diagonal. The diagonal term dictates the behavior of the time average of the expectation value of this operator O. The off-diagonal term encodes how the expectation value at time t can fluctuate over time about the mean. This coefficient out front makes the hypothesis consistent with the Wigner-Eckert theorem. And now all parts of this hypothesis depend on spin quantum numbers. That's our non-abelian eigenstate thermalization hypothesis, incorporating non-commuting charges into the eigenstate thermalization hypothesis. And we'd like to use it to learn about thermalization. Again, here are the premises in the conventional argument from the eigenstate thermalization hypothesis to thermalization. We said there are three premises. We've now resolved our problems with two of them. But But we still have a problem with microcanonical subspaces, as we discussed a number of minutes ago. We need to generalize this notion. I know that the request was for a 45-minute talk, so I will skip the next slide. But the basic idea is we can generalize the notion of a microcanonical subspace. That was done in some earlier papers.
We have extra time, so don't worry about time.
Okay, good to know. But yeah, the takeaway is we can generalize the notion of a microcanonical subspace to make it consistent with non-commuting charges. So suppose that we use our non-abelian ETH, we have a Hamiltonian and an operator that satisfy it, and we prepare a quantum many-body system in this generalized microcanonical subspace. We would like to infer about thermalization. So we want to compare the thermal expectation value of this operator to the time averaged expectation value. The thermal expectation value is the trace of the operator with the appropriate thermal states, in this case, the non-abelian thermal states, the NATs. The time averaged expectation value we construct as follows. We suppose that the whole system is prepared initially in one of these generalized microcanonical subspaces. Then consider calculating the expectation value of the operator at some time t prime, and then averaging over time and taking the limit as the final time approaches infinity. That is the time averaged expectation value. Let's compare the two different types of averages in two different regimes. First, let's suppose that the magnetization of our system is as large as possible. It grows like the system size. In this case, one can prove that the time averaged expectation value minus the thermal expectation value is just as small as usual. The corrections grow like 1 over this global system size. This is the scaling, you might recall, that we observe in the absence of non-commuting charges. So we qualitatively recover a result that is associated with just ordinary thermodynamics. But the proof was a lot harder in the context of no non-commuting charges. The proof takes about a page, and in this case, it takes a few appendices. Now let's go to the opposite extreme and suppose that the system's magnetization is as small as possible. It vanishes. Under certain conditions, one can show that the time averaged expectation value minus the thermal expectation value now is like 1 over the square root of the total system size, which is polynomially larger than the usual correction. And I should mention that we can draw this conclusion under an assumption that we argued is physically reasonable, but needs to be checked numerically and ideally experimentally someday. So the corrections are larger than usual, so the system in some sense is able to refrain from thermalizing, getting quite as far down as usual toward the thermal state. So this result has a fundamental and a possible practical implication. First, the system doesn't get quite as far down as usual toward thermalization, then the system, in a sense, doesn't feel the arrow of time quite as strongly as usual because of the close relationship between thermalization and the arrow of time. And second, if the system doesn't get as far toward thermalization as much as usual, then maybe it retains some extra information about its initial conditions. And maybe we can use that retention in a quantum memory, say for a quantum computer. Does anyone have a question about this part of the talk?
Throwing some molasses in on the system so it can't thermalize as fast. There's some hesitation on it because of this non-commuting. That's what this is saying. Is that an interpretation of what you said there?
The idea is if a system has non-commuting charges, then maybe it doesn't thermalize as much as usual as a function, as in maybe thermal predictions are not as accurate as usual as functions of the size of the whole system, rather than as functions of time. So suppose that I have a really small system. It's really far from an ordinary, a conventional thermodynamic system, because a conventional thermodynamic system is infinitely large. And if I have just a really small system, then I might not expect thermodynamics to work very well, because information can bounce all around. So I'd expect some recurrences that happen on not too long a time scale. As my system grows larger and larger, it approaches the thermodynamic limits. And so I expect thermal predictions to get better and better as functions of system size. So that's the sort of dependence we're talking about here.
Yeah, when you talk about a small system and a large system, and okay, what value of n are you talking about when you're talking about a small system?
I guess I could answer that question in two ways. One is when I was just illustrating with my hands here in response to this question. And one is what sorts of values for n did we use in numerical studies? So when I was just illustrating with my hands here in response to the question, the number n didn't matter because we were just talking about how the accuracy of thermal predictions changes as a system grows and toward the thermodynamic limit. When we were doing numerical situations, primarily my postdoc, Alec Lasek, he was using system sizes of approximately 8 to 20 quantum two-level systems, because those were the systems whose properties he could reasonably calculate using the computing resources he had.
Yeah.
But if we could use one of today's quantum computers, then maybe we could get a few tens more qubits into our calculation.
But I haven't read the paper. Did you look at how the results scaled as you went from, say, 4 to 6 to 8 to 10 to 12? I mean, could you see actually the change in the results as you increased n slowly?
That is a goal for a future paper. Our paper was more basic. We were just checking, does the non-abelian eigenstate thermalization hypothesis appear to accurately describe some Hamiltonian and some local operators? So that paper was on a step that we needed to take care of before the study that you described, which I think is a very good goal that we would like to get to.
Oh, okay, thank you.
Sure.
My brain understands it more in the terms of the thermodynamics of 1800s. So if you have a system and there's an anomaly in the middle, it's hotter. But the particles can interact and they have this non-commutation problem. If they didn't have that problem, I would expect that in 10 minutes, this would be thermalized and everything would be the same temperature. But are you saying that it's not going to be thermalized and there's going to be significant variations in the temperature of this object because of this non-commutation?
That's something we'd like to know, but I'm comparing a thermal prediction to a time average prediction. So my time average does not depend on any particular time. My time average results from averaging over all times. Okay. So the results I'm presenting here do not tell us anything about the process of thermalization in time.
Okay.
That's something that we would like to, that's another thing that we would like to get to later.
Okay. Okay. All right. Thank you.
And it is very much something that I would like to know. So I am a fan of that question.
Okay.
There are, as was indicated by recent questions, lots of opportunities in this little subfield. One is we now have a puzzle. We have a small pile of evidence showing that the non-commutation of charges hinders some features of thermalization, but we also have a small pile of evidence indicating the opposite. We just saw 6 pieces of evidence showing that the non-commutation of charges interferes with some features of thermalization. But suppose we have a quantum many-body system and the particles are interacting, they're thermalizing with each other, they entangle with each other. The generation of entanglement is an important part of the thermalization of a quantum many-body system. But we studied how the non-commutation of charges affects the average entanglement in a system, specifically average bipartite entanglement between two parts of the system. And we found that the non-commutation of charges enhances the entanglement, and so amplifies a feature of thermalization. Also, there is a regime of matter called many-body localization that a quantum many-body system can be in, and this quantum many-body system behaves in the way that you would expect. So it thermalizes very slowly. Suppose that you measure the particles' positions. The particles will approximately stay in those positions for a long time afterward. They take a long time to spread out, and they take a long time to entangle with each other. Now you can take a many-body localized system and force it to conserve non-commuting charges by tweaking the Hamiltonian. And if you do this, you destabilize the many-body localization. But even a tiny perturbation that breaks the symmetry will break the many-body localization and cause the system to thermalize quickly. Finally, I'm proud of this paper, which I did not author. My first PhD student authored it all by himself. He studied a system that can have certain algebraic properties called dynamical symmetries. If a Hamiltonian has dynamical symmetries, then certain operators are protected from ever thermalizing. My student showed that you can take one of these Hamiltonians that has these algebraic structures, you can force it to conserve non-commuting charges, and as you force it to conserve more and more non-commuting charges, you eliminate these algebraic structures, and so you eliminate the protection on any operators from thermalizing. So if you force non-commuting charges, if you force the Hamiltonian to conserve non-commuting charges, then it will thermalize essentially all operators. So we have these results indicating that non-commuting charges can hinder and enhance features of thermalization. These results don't technically conflict with each other because they were derived with different specific setups, but conceptually they conflict with each other. So we need to reconcile them. In case you couldn't tell, I'm more of a fan of the hinder category. So I kind of hope that that will win out in the end, but we have to see what happens.
You have a horse in the race.
As much as a theoretical physicist can.
Right.
I also think that we now need to go to every feature of thermodynamics and chaos and ask, what happens to it if the dynamics conserve charges that don't commute with each other? Is there a change? And if so, what is the change? There are lots of features to think about in thermodynamics and chaos, in part because quantum information theory has recently been used to define and measure different features of quantum many-body thermalization. Also, a lot of the work on this little subfield has been done within the intersection of quantum information theory and quantum thermodynamics. So now is a good time to spread the ideas to other fields of many-body physics, like atomic, molecular, and optical physics, condensed matter physics, maybe even quantum chemistry. In summary, we talked about this little subfield of non-commuting charges in quantum thermodynamics. We said that we can take an undergraduate statistical physics setting and add one little tweak related to non-commutation. Our expectations about thermalization start breaking down. We talked about a concrete example of a chain of spins that have X, Y, and Z components of spin that are conserved. We talked about features of thermodynamics that change if charges fail to commute, especially the eigenstate thermalization hypothesis, which we generalized. And we can use it to show that in some special cases, we might expect thermalization to take on an anomalous scaling character in the presence of non-commuting charges. Finally, there is a lot left to be done. So this is the review that I mentioned. If anyone is interested in getting into the subfield as a whole, my group has been fairly obsessed with this little subfield for a number of years, so this is all our work. And if you're interested in more of a story about how this subfield arose, then I can point to chapter 12 of that book. It's more of a narrative. So, thanks very much for your time. And I'm happy to take more questions.
So not that I understand all of what you're saying, but it sounds like if you could put objects into a situation where they're non-commuting in a quantum computer, they may last longer.
That's ultimately the hope.
Oh, okay. That's all right. I mean, I could see that it's leading to that. And the question is still, as you phrase it, you're averaging over doing it, looking at it in different ways. So the fact that there's differences in terms of understanding how quickly something thermalizes versus time averaging versus other thermalization processes.
We have a little bit of evidence suggesting that maybe thermalization is slower in the presence of non-commuting charges. This is the trapped ion experiment. So our experimental friends performed this experiment with non-commuting charges. They saw the system approach the appropriate thermal states. And then they performed an experiment with just commuting charges, and they observed the system approach the appropriate thermal state. And the approach was slower in the first case.
Oh.
But in one case, there were 4 charges. In the other case, there were 2 charges. So the comparison wasn't fair. But it's the suggestion of a possibility.
Oh, okay. All right.
We definitely need follow-up work.
Okay.
So,
Go ahead.
there was in Callan's book, I guess he generalizes Jesus' idea that you can do thermodynamics from a few postulates at the beginning. Is this inconsistent with that, or is it you have some new postulates that go into it in addition, and then you can turn the crank like they did?
But first, I'm glad that you mentioned Callan's book, because that is quite possibly my all-time favorite textbook. I guess I would have to review their postulates. I can say that something that we found is in some important thermodynamic arguments, there's an implicit assumption that quantities that are conserved globally and transported locally commute with each other. And that is an assumption that we do want to eliminate, or that we've eliminated in this work and that we would like to eliminate more broadly. Did somebody online have a question?
If a system fails to thermalize because of non-commuting particles, what is the proper substitution for temperature in such a system? Would you have multiple temperatures for different components like we do in plasma situations, or do you have some substitution for temperature?
Let me go back to a previous slide and then share my screen again. I think that would be most useful.
Can I ask a simple question?
Well, is it all right if we address the previous question first?
Yeah,
Thanks.
well, I didn't really understand the talk that much. but if what you are saying is right,
Is it all right? Is it all right if we address the first question first?
yeah, let me ask a question, and then you can say. Um,
Go ahead.
Okay, thanks. So we find that the system, even in the presence of non-commuting charges, approaches a thermal state associated with a temperature of the sort that we're used to. So here's that thermal state. Our question is, well, the question that we have been considering is, does the system get as close to the appropriate thermal states as usual, as in the absence of non-commuting charges? And another good question is, does the system thermalize as quickly as usual? So it seems that we've observed there is good reason for writing down this thermal states, and the system thermalizes toward this state. We're just the system might not get all the way down to this state quite as far as usual. And so we can define this temperature as usual.
Okay.
And
Does
then we
this
have
have
a,
anything to do with the glass transit? I mean, does this apply in some sense to the slowing down of the dynamics in a glass transition? Could it be related to that?
I think that glasses form a great example of another mechanism by which thermalization can be slowed down. I think of this line of work as kind of an attempt to see if non-commuting charges can form another mechanism similar in nature to glassy dynamics in altering the nature of thermalization or changing how or to what extent a system can reach full thermalization.
Interesting. Thank you.
well, there's no other questions, and thank you
Does
very much
Passive
for,
have a question
Oh.
now?
somebody had a question?
No. Okay. No more questions, Jerry.
Okay.